Like me, you've probably read about Hornady's DVRT, that is, drag variability reduction technology. That technology was developed using Doppler radar and Doppler radar research. In essence, these bullets, like the Hornady A-tip, are designed to have reduced drag variability, not necessarily reduced drag, but reduced drag variability. And the reason why that's important ties back to some other research that has been done looking at improving military sniper rifle bullets. And that paper indicated that drag variability is a critical component to ensuring high precision and those one-shot cold bore kills on target as desired, obviously, by the military. Now, really, this all ties back to what I and others have been saying for years, and that is consistency equals accuracy. So, in other words, consistent drag equals accuracy. So that got me thinking once again. Now, I have a Labradar Doppler radar, and while it's nowhere near as sophisticated as the Doppler radar units used by Hornady and by the military and by ShyTac years ago, all this stuff, it does still provide me with some track of the bullet as it flies downrange toward its target. Now, realistically, I'm getting about 70, 80, sometimes 100-yard tracks, and I know that that's not ideal, but I still wanted to take a look and see what can I see from studying those bullet tracks from my lab radar. So I downloaded those tracks from a bunch of my different shots and trips out to the range, and the first thing that I did after downloading that data is I calculated the drag coefficient along the path of each of those shots fired. Now, a drag curve should look like this. Along the x-axis, we have the bullet's velocity. Now, notice it's normally given in Mach, and also understand that the fastest velocity, essentially the muzzle velocity, is all the way on the right side, and the terminal velocity is on the left side. Drag, or the drag coefficient, is on the y. At the muzzle and at those real high velocities, drag is relatively low in contrast or comparison to other points along the bullet's flight. As the bullet slows and nears the speed of sound, drag increases. Then, as the bullet passes through the sound barrier and goes subsonic, drag once again drops. Now realize the lab radar can only track bullets essentially from the muzzle to about, at most, 100 yards. 100 yards might even be pushing it. That's well inside that supersonic velocity zone, and really only a very small part of this idealized drag curve. Okay, I realize all this, but still, I think it will be fun to take a look at how this particular bullet, the Hornady A-tip, how does its drag curve look in relation to that idealized drag curve. Now, I'm loading this 230 grain Hornady A-tip for my 300 PRC, but I'm also loading another bullet for my 300 PRC, and that is the Berger 220 grain long-range hybrid target. So let's look at that one as well. And here's what I first saw. A lot of pretty much meaningless noise. But that very likely is because these first tracks that I plotted were very short tracks, maybe only out to 20 meters or so, and that bullet never had the opportunity to settle down. But I've got a lot of tracks. Oh, I kept calculating the drag coefficient and plotting those on the graph. And I then began to notice a trend. Some of the shots followed the expected drag curve quite nicely. Others did not. The trend that emerged was that the slightly slower bullets followed a more smooth drag curve, while the fastest bullets showed a lot of variability, I'm not going to call it noise, because the signal-to-noise ratio of every one of these points that I plotted were really strong. Signal-to-noise ratios were higher than the value of 12. So that's kind of a rule of thumb, by the way. If you're ever looking at those tracks on your Labradar, the meaningful ones, the good tracks, the good records of data, have a signal-to-noise ratio in excess of 12. So every one of these points that you're looking at had a nice, strong signal-to-noise ratio, but yet we're seeing a lot of variability in the actual drag coefficients of those bullets that are flying the fastest, moving the fastest. Now that makes me recall some earlier conversations and reading that I've done on intermediate ballistics. Now a lot of us are familiar with interior ballistics and exterior ballistics and terminal ballistics, but maybe not familiar with what's called intermediate ballistics. So interior ballistics is all the stuff that happens inside the case as that round is being fired and as that projectile, the bullet, is traveling down the bore. Exterior ballistics officially begins as the bullet exits the muzzle and then begins its flight downrange toward its target. Intermediate ballistics actually looks at that point from when the bullet first leaves the muzzle until the first few yards, sometimes even less than that, the first few yards, maybe even a dozen yards of its initial flight. And the reason why a lot of work has fairly recently been done on intermediate ballistics, some of that is because of the popularity and interest in suppressors or silencers. What effect do they have on precision and shot dispersion? Muzzle brakes, flash hiders, these sorts of things. But also just trying to understand what are the various different factors that affect that bullet's precision or dispersion on target downrange. You may have heard that sometimes on a bad crown on a rifle that the gases are escaping inconsistently. Maybe the gas, let's say, on the bottom of the bore are escaping faster than the gases escape on the top, simply because of some errors or problems in the crown of that rifling. But what happens then is the gases that are escaping early are pushing up on that bullet, potentially or theoretically, and causing that bullet to move slightly in its overall path. And if that's not consistent, shot to shot, well, that worn out crown can really cause increased dispersion on target. So there's something to that first few inches, maybe first yard or so, or first few couple of yards of that bullet's flight, and that's called intermediate ballistics. So if some of these tracks that are showing bullets with high drag variability are indicative of bullets that are exiting more erratically, in comparison to those bullets that exhibit a smoother drag curve, which could be indicative of a more consistent ejection of that bullet from the muzzle, resulting, at least hypothetically, in a more precise group. So I took a look at the drag curves for my load workups. Now, if you've been watching this season of Extreme Reloading, you were with me when I did all those different load workups. And you'll probably remember that we looked closely at optimal charge weight methodologies. We also looked at harmonic node methodology to identify the ideal powder charge for these two particular bullets. Well, perhaps a third approach is to use Doppler radar. So I studied the load workup for my Hornady 230 grain A-tip bullets, and I noticed somewhat slower muzzle velocities, that some of those tracks were nice and smooth, very nice and smooth. One of them of interest that gave me a very nice smooth drag curve, had still a good muzzle velocity, and when I looked up the powder charge, that powder charge was 73.5 grains of H1000. What's interesting is that is precisely the powder charge that I'm using, and that was identified as a harmonic node. So that's kind of interesting, kind of good to see that. And maybe I'm on the right track here. For the 220 grain Berger bullets, the Doppler method suggested that I be using a powder charge of 75.1 grains of H1000. Now that is fairly different than the powder charge that I was using. And in reality, it really didn't turn out that great for me anyway. I had standard deviation of muzzle velocities in the teens. The groups did not beat Hornady A-tip, and so I think it's maybe worth a try. So here's what I'm going to be doing. In just a little while, I'm going to be heading out to the range, and I'm going to be loading 10 rounds of this Berger 220 grain long-range hybrid target. And I'm going to be using the Doppler method approach of 75.1 grains of H1000. And I'm going to load 5 of those rounds into the Peterson brass, 5 of those rounds into Lapua brass, shoot 2 groups at 100 yards. Come along, head out to the range with me. We're going to see how this goes. Then we'll come back in and find out if I'm on the right track or did I just head down the rabbit hole for naught. Target at 100 yards. First group with these 220 grain Berger bullets will be loaded in the Lapua brass, bullseye on the left. Lapua on the left. That's 5. We'll get ready to shoot the next 5 group, which will be again the same bullet, but loaded in Peterson brass on the right bullseye. That's 5. Back on safe. Drop that mag. Well, that's pretty interesting, wasn't it? Let's dig into all these data that we just collected to find out if the Doppler method of load development actually improved the precision of this 220 grain Burger bullet in my 300 PRC. Here we're looking at a summary table of all of these results. The first 2 data columns show my previous load workup results using the optimal charge weight method. The next 2 columns of data show the Doppler method of load development, and in both instances we're looking at the Lapua brass on the left, Peterson brass on the right. Starting near the top, we're looking at the extreme spread of those 5-shot groups measured in MOA, and what we're seeing there is that the mean extreme spread has been improved by about 15%. In other words, we went from a sub-MOA group of 0.92 MOA down to a 0.78 MOA group. Mean radius using the Hornady-Fordorf group calculator also showed an improvement. The grand mean radius, that is simply where we take the mean of the mean, and in that statistic again we're seeing an improvement from 0.36 down to 0.27 inch. Now the muzzle velocity, you might look at that and say, oh, but look, you had a reduction in your muzzle velocity. Yes, that was absolutely anticipated because the powder charge under optimal charge weight was fairly higher compared to the charge weight used with the Doppler methodology. We talked about that in the beginning of this video. So I'm not concerned at all about that, and in fact, I still achieved my goal for this particular bullet of getting at least 2,800 feet per second at the muzzle. Let's go back to that table and look at the next record of results. Here we're looking at the standard deviation of those muzzle velocities, and in our previous video, I wasn't too happy that we were not in a single-digit range. We were well into the teens, as you're seeing here. In fact, the mean standard deviation of those 2 groups was 16.4, almost 16.5 feet per second. For a long-range precision rifle, that's actually not acceptable, at least to me. But now, under the Doppler method of load development, we are down nicely into that single-digit range, 7.9 feet per second. That is a 52% improvement by using the Doppler method. Now that's all very good to see, but now let's go back and take a look at those drag curves produced by these 2 new groups. And this too is interesting. What we're looking at here is the drag curves for the rounds loaded into the Lapua brass, and overall they're actually quite smooth. And many of these were tracked all the way out to 90 yards or more. Shot 3 is looking a little bit squirrely. Some of those, as they're leaving the muzzle, look a little bit variable, a little bit too much variability, one could say. But I've had some conversations with some radar specialists on this exact thing that we're looking at here, and they told me that oftentimes they see a lot of variability in the drag calculations when that bullet initially leaves the muzzle. And that may be that settling down period that occurs out to the first, X number of meters. In this case, probably only, 5 or 10 meters or yards after the bullet leaves the muzzle. Now, if we go back to that graph, looking at shot number 4, that is more or less picture perfect, exactly what we should be seeing in a nice, smooth, well-behaved bullet. The drag curve for the shot string fired using Peterson brass, loaded with Peterson brass, we're seeing 3 of the 5 shots look very good once again. But shots 3 and 5 on the top half of that graph, they exhibited what I would call a relatively abnormal drag curve, a little bit problematic. Now what's interesting is that both of these rounds 3 and 5, also exhibited or had a fairly higher than normal muzzle velocity. And that's what we're looking at right here. Notice round 3, 2,831 feet per second. Round 5, very similar to round number 3, but not quite as fast, 2,826. All of those rounds, all the other rounds, were hanging in there around, you can see 2,815, 2,806, just kind of breaking that 2,800 feet per second threshold that I was looking for. And if we go back to the target, shot number 3 also exhibited a different point of impact on that target. In fact, if I were to eliminate shot number 3, or if I fired that and it exhibited a more well-behaved bullet drag profile, I wouldn't doubt that shot number 3 would have impacted down here with the rest of the bunch, thereby producing just a fantastic group that probably would have beaten the group fired using the Lapua brass. In all cases, it's still the Berger bullet. So overall, I'm really happy with this new approach to load development that I discovered using this Doppler radar methodology. And what do you think? I'm interested in hearing your thoughts on this whole approach using Doppler radar to help us determine a good load workup. And if you're interested in trying something like this and need a little bit of help, certainly post that into the comments. I have developed an Excel spreadsheet that will very easily allow you to calculate the drag coefficient for every one of the rounds that you're firing through or across the lab radar, just using those track records that are available when you download the lab radar. In fact, we have an entire video explaining that process. I put a link in the description so you can access that video and download the drag calculation Excel spreadsheet. So post those questions in the comment section below, and thanks a bunch for watching.